Hey, this is Jonathan Templin back with you for another lecture. This time, a brief introduction to missing data methods. Here we go. So this is really intended to be a broad overview of missing data. It's a very rich, deep literature base on how we handle missing data. And the goal today is really to build an intuition, introduce vocabulary, and demonstrate a couple different ways that we handle things in a modern sense. This is really not an exhaustive list. In fact, I taught a whole semester class on this just a couple of years ago, and honestly, you could probably spend more than a semester on the topic itself. But as this quote by Little and Rubin note, the problem of missing data is one of the most pervasive in the practice of statistics, and we're going to see why as we go through this. So what we're going to do in this lecture is talk about why missing data matters. It's not just inconvenience, it's a pro tip there. We're going to talk about a taxonomy of types of missing data. And these acronyms you see here, MCAR, which stands for missing completely at random, MAR, which means for missing at random, and then MNAR, missing not at random. And we'll talk about what they mean because it's clearly not obvious. I mean, missing completely at random versus missing at random. How does that work? Talk about that in a few slides. I'll mention a little bit of the old ways of handling missing data, and I'm guilty of these myself. Particularly, I remember my first statistics program I pulled up. I think it might have been like SPSS way back in the 90s. And the missing data box was like, yeah, impute the mean. Let's see why that is actually not a good way of handling missing data. We're going to talk about modern method number one, how we use full information maximum likelihood with missing data. I've talked a little bit about this before, particularly in the context of building our multivariate normal likelihood function. This implements it just briefly. And then modern method number two, which is multiple imputation by chained equations. Now, in the context I'm giving this, these are almost equivalent, but there are places where they slightly deviate depending on the models that you use for each of these. And then finally, a little bit of practical guidance as we wrap up. So let's talk about why missing data matters. As you know, real data almost never complete. A lot of reasons why you may have missing data. You might have survey non-response, and that non-response may be linked to certain groups or certain types of statuses of individuals in the data set themselves. There could be attrition in longitudinal studies. It means it's hard to collect data from a person one time, let alone multiple times. You could have instrument or sensor failure. If you have an app that's supposed to collect data and all of a sudden you have a glitch with the network signal, the app may not send a reminder to the person, or you may not receive the data. You have routing and adaptive questionnaires. Maybe you get the wrong questions answered by the wrong people. Or you could have a difficulty in merging data from multiple sources. The danger, though, is that most software defaults to complete case analysis, therefore dropping rows with any missing values quietly. And that is not a good situation to find yourself in. Now, there are two big consequences of mishandling missing data. The first is bias, and the second is inefficiency. Stop me if you've heard this before. If you do something wrong, the numbers you get may be wrong systematically. That's bias. Or you might inflate or change your standard error. And remember, parameter estimate divided by standard error is commonly used as a Wald test for determining statistical significance. So if either of these are wrong, you can imagine what happens to your hypothesis tests and your significance tests as well, too. Now, here's an example of a simple linear regression where X is predicting Y. I don't even have the name here. You can see the true value of the data and the complete data analysis here, where the true fit, the dashed line, and the red line, the observed fit, are roughly equal. Whereas if we ignore missing data, we might see a discrepancy between the line itself. And this is not even considering the standard error around that line as well, too. So even a moderate amount of non-random missingness visibly biases our estimated regression coefficient. That's a problem. So there's a taxonomy of missing data that was largely attributed to Rubin in 1976 that we still use. It's not the most interesting or the most useful, but it does provide a mathematical basis for how we do things. There are three mechanisms. The first we're going to talk about is something called missing completely at random. And so to do this mathematically, let's just imagine Y is a full data matrix and R is an indicator matrix, where the element was whether or not the observed value in Y is missing or not, right? So if it's observed, R has a 1, and if it's not, R has a 0. So the definition, mathematical definition of missing completely at random is that the missing data do not depend on R, basically whether an observation was missing or observed, does not depend upon the data itself. So you can think of this as something like missing based on a coin flip, missing based on a random process, missing based on an internet glitch or a battery failure or something along those lines that has nothing to do with anything about the data. Turns out this is not necessarily a terrible situation to be in, because as it doesn't depend on the data, turns out this missingness saps your power but doesn't necessarily bias your results a whole lot. Then something that sounds very similar, but it actually functions a little bit different, is that missing at random, or MAR. So missing at random, which sounds a lot like missing completely at random. Missing at random says that the probability of observations being missing is due to observed data that you have collected, but not actually the missing values themselves. So in this case, let's imagine you have a whole data set, and for whatever reason, maybe one of the groups is less likely to answer a question, but you have the group variable itself. So now you can sort of allow yourself to sort of correct for that group missing data based on analyses or methods that we're going to show later on. So missing at random is correctable, is fixable, and that the modern methods that we use really try to address this. The third mechanism is missing not at random. This is where the missing data itself depends not only on data you've collected, but potentially data you never collected in the first place, including missing values themselves, right? So if a person doesn't want to respond because basically the value itself may be not something they want to disclose, maybe some sensitive information or so forth, you're in this situation. And unfortunately, missing not at random is a very difficult difficult case to have to deal with. Missing not at random takes highly specialized and models or methods, a lot of which depend on assumptions that you must write down ahead of time. So one thing I will note is that missing completely at random is a special case of missing at random. So that is helpful, at least going forward. So here's an example of missing completely at random. Let's imagine we have a set of y and a set of x's, and we just have a 30% missing, and they're missing because of just some random process. You can see that the mean value for mean of x for anybody with a y is roughly equal to the mean of x for anybody without a y. Right? So under missing completely random, observed and missing groups that look very similar on all the covariates, and it turns out Little created a test for this, a statistical test for this. You can find it in the NANIR package right here. This thing will allow you to test whether things are missing completely at random. Basically, you're testing whether these means are the same or are they different. Although I will say it has low power and small sample sizes. Now, with the same idea under missing at random, missingness depends on some of the observed variables, but not on the variable that's missing itself. So let's imagine we have about 48% or 49% of our data missing. In this situation, our means would be a little bit more different from each other. So for missing y, the mean of x may be positive 0.493, and for observed y, the mean of x may be negative 0.5. Right? So x itself predicts missingness. But once we condition on x, so once we know that x does that, once we control for x, then missing becomes random again. And the key implication here is that methods that use the full covariate structures, such as FIML, full information maximum likelihood, or MICE, multiple imputation by changed equations, can recover unbiased estimates under missing at random assumptions. So if your data are missing at random, using one of these methods will make sure that you get a more accurate result. Now, missing not at random, this is where the missingness depends on the unobserved values themselves, even after conditioning on all observed data. In this case, you might see a very widely discrepant value for this missing value of y for observed versus true itself. So basically, in this case, if we have, again, about 48% missing, our mean of y that we observed was negative 1.266, but the true y may be actually much higher. So this would be a case where those who have higher values of y may not want to give you their answer. So how do you impute, how do you go and figure out what that might be? Unfortunately, neither of the methods I'm going to talk about at the end of this lecture provides a general solution. Addressing missing not at random often requires something called a sensitivity analysis, so basically changing assumptions, seeing how much it changes your result, plus explicit models for the missingness mechanism. So why is it you have to hypothesize why someone may not give you the data for a certain variable or set of variables, model that, and then see what the result happens to be. You can guess that might take a crystal ball. Unfortunately, if you're like me, you don't have one. So here's an example of the plot of missing data. You can see the observed values are the blue dots. The x's would be observed. Those are the true values, but they were taken as missing in the data set. And you can see under missing completely at random, they're spread throughout the scatter plot of x and y values. At missing at random are more likely to happen when x is on the high side. But again, we might see that. And missing not at random, right? The y values might be missing when they're high by themselves. So this kind of shows the three mechanisms to you in a plot. Now, there were some worse ways of doing missing data. These tended to come in many, many years ago, but you still see them in place somewhat today as well. The first one is to literally listwise complete case delete data. Basically, drop any observation with a missing value on any variable in the model. So let's imagine you have a 5-variable path model. Somebody doesn't give you data to one of those variables, maybe variable 3, but they have all the other variables. Turns out they get removed from the analysis. Therefore, you could end up deleting a whole lot of data. The problem is that to use listwise deletion, you have to assume missing completely at random for unbiased estimates. And this is a rarely justified assumption. Furthermore, you lose substantial power, particularly in wide data sets with many variables, right? Because the more variables you have, the more likely it is one or more are missing. Right? And you may end up having a situation where everybody has at least a little bit of missing data. So listwise deletion is something where you have no data. Not a good idea. Another approach that was difficult, that's also difficult, is pairwise deletion. If you're getting a sense of a trend here, and deleting any of your data, not usually the best idea. Now, pairwise deletion is the case where, for instance, if we have a correlation matrix here, our data that are input to give us a correlation, let's say between x1 and x2, are the observed values for both of those variables. If a person is missing either x1 or x2, then they'd be removed from this specific correlation. Whereas if they had both x1 and x3, they might be included in the other correlation itself. Now, the problem is that with this is that each correlation then uses a different subset of the data. Right? The resulting correlation matrix itself may not be positive semi-definite. You may have heard that before. Positive semi-definite means that this thing can be inverted. Right? Technically, it means that the determinant of this matrix is 0 or greater. Bad idea if we're using analyses that involve the inverse of a correlation matrix. And it turns out most of the methods that involve normal distributions will do that. Right? So you end up in a situation where FCM or path models may fail or produce nonsensical results if your input to it is a correlation or covariance matrix. Another method that is commonly used or has been commonly used is to simply replace each missing value with that observed variable's mean. Turns out, right? So here, right here, the problem is that this artificially deflates the variance because basically you're plugging in all variables with the same value. That same value has 0 variance itself. So you end up finding quite a bit of smaller variance, which will end up causing issues with standard errors later on. Plus, it also distorts the distribution itself. You might have a spike at the mean, meaning all the missing data show up there. That also causes problems when we think about normality assumptions and so forth that might apply in some of the models that we're using. Another approach that was problematic is to basically take a regression, basically come up with a predicted value for your missing values, and plug in that regression's predicted value. Now, this is slightly better than mean imputation because now you won't have all values being the same itself for missing data. However, a single imputation that uses a point estimate does not allow for you to incorporate uncertainty. And uncertainty is a problem is sort of the key to understanding how we allow missing data to be present in our models. The idea is this: If we plug in one value for that missing data, it's like we're super confident that our response is that person who omitted that response, we know exactly what that value is. In reality, statistical models don't work that way. And a lot of what statistics does is quantifies the uncertainty in in our estimates. And the same thing is needed when we plug in data as well. All right, let's get into one of the methods that does work pretty well. This is full information maximum likelihood. Under FIML, also called direct maximum likelihood, sometimes raw maximum likelihood, each observation contributes to the likelihood using only its observed variables. Right? Imagine this. If you had a multivariate normal distribution, let's imagine we have a path model and we assume this multivariate normality. We have 5 variables in it. We have a subject that gives us variables 1 through 4. In that case, the likelihood function for that subject will not be 5 dimensions. It'll be 4. It'll be 4 dimensions, basically 4 variables. The omitted variable is dropped, and the remainder of the covariance matrix is used, basically using what we end up having. Right? So no data are deleted, no data are imputed. We just use what we do, and our likelihood function adapts to the size of the data that we end up having. So the full model is estimated simultaneously with the missingness put in place. So again, this is the likelihood function. This is your multivariate normal log likelihood right here, or actually approximately equivalent to it. It's not exact. Basically, we can resize our covariance matrix and our mean vector to fit the number of observations we have for each case, but then we still use the likelihood as if it were the full likelihood function itself. So the key advantage here is that full information maximum likelihood uses the covariance structure to borrow strength from the observed variables to recover information about the missing ones. And it's all within the model itself. So this is a really convenient way of making it work. And when you can use it, it turns out to work out quite nicely. So for instance, we might have a path analysis here where we have a 3-variable path model where x1 is predicting x2 is predicting y, and then x1 has a direct effect of y. This is a typical mediation path. x1, you might say that the relationship between x1 and y gets mediated by x2 here. And you can end up seeing the path coefficients here. We may have 500 observations. Now, let's imagine we introduce missingness in y and x2 that both depend on missingness in x1 right here. So we might have 28% of cases missing in y, 17% in x2, and we might have a total of 291 complete cases. About half the sample is incomplete. So complete case analysis would throw away a large fraction of these observations. You can imagine what that does for your power, even if this were missing completely at random. But when we impute this, if we use the complete case method, we can see here's an example of our true values and estimated values, their standard errors, and the bias as well. And what you end up seeing is in this example, our true value, our bias is slightly lower to quite a bit lower in each of our cases, in our complete cases. But in FIML, the standard errors are more appropriately sized. They're a little bit bigger, and that's because we have a little bit bigger sample size, but they're not completely bigger itself. And here's an example of that in a plot. So in this case, using this example with Levon and a path model, we assume multivariate normal data, and we can get away with this. Now, if you don't have multivariate normality, there are other ways that you can build in full information maximum likelihood, but they take a lot of effort usually. I had gone over some of those in my previous class on missing data, and if you want to find that, you can find it on my website in my previous classes. This works within the model itself. Missingness is handled at the model level, so we don't have to pre-process our data. You're going to see that in the next step in multiple imputation by changed equations, we actually do a lot of pre-processing of our data. And here we're assuming missing at random. So if the data happened to be missing not at random, those estimates would still be biased. Now, I would find this to be best for structural equation model and path analysis. Right? If you're already in that Levon or SEM framework, this is an easy choice to add into your analysis as well. And finally, you're going to see this again as a comparison to our next method. There are no imputed data sets. This is just the data. That's how it works. Results cannot be used outside the model. If you need imputed data for downstream analyses, you might have to use mice. So this is a positive in many ways because you're going to see under multiple imputation by chained equations, things get a lot more messy. But let's get into mice. There are three stages of multiple imputation by chained equations. And these three stages essentially equate to doing multiple analyses on your data, but basically on different versions of data sets where you've imputed values. So stage number one, we're going to create little m complete data sets by drawing from the conditional distribution of each missing variable given all others. Right? So basically we're saying that each variable gets its own imputation model. Let's parse this a little bit. Let's imagine this 5-variable path analysis that I've been hypothetically talking about throughout this lecture. In this case, for variable 1, you would predict its value using a linear model where variables 2, 3, 4, and 5 are predictors of it. Now, instead of imputing the predicted value, what you would do is draw an imputed value from the predicted distribution. So each person will not only have a predicted score for that variable, they'll also have a standard error of that prediction. You can then assume a normality. Using the assumption of normality, you can draw from that predictive distribution and impute the score. So for each of these m complete data sets, we are drawing a new value from this distribution. Now, I will note in the imputation phase, though, we can't just do this once because the prediction of x1 based on x2, x3, x4, and x5 will also be biased because we have missing data in the other variables. So what we end up having to do is do this process over and over again. Impute x1, impute x2, impute x3, and so forth. Those are the chained equations. Then after we predict all 5 of those variables, we go back and rerun those analyses over again, but with the imputed data included. That allows us to have a wider error with each imputed value because each of the regression coefficients themselves in this imputation are likely to be biased from the missing data. So the chained equations approach relies on a Bayesian-like algorithm where every iteration you basically impute all missing data as variables, and then for the next iteration, take what you just imputed as real scores and do the same process over again. And you do this process thousands of times, but then you take from those thousands of data sets a smaller sample of m. Then, once you have little m data sets, the next step is to apply your model of interest to each of them. And if your eyes are glazing over thinking, that's a lot of work, yeah, it is. But basically, we have to go and estimate a model for each data set because we don't have a clear way of understanding how that data set functions. Now, I will note, this is a maximum likelihood-based idea, or a least squares-based idea. There are some ways that you could come up with in Bayesian methods where you wouldn't necessarily have to fit m separate models, but that's not for this class. That's the deep dive that you may want to get into later. But now, if you think about it, at the end of step 2, we have m sets of results. The third step is to pool those results using something called Rubin's rules. The Rubin's rules will then produce a single set of estimates and standard errors that reflect both within and between imputation uncertainty, allowing you to then report those results of the missing data themselves. Okay, so the key in the mice algorithm is this. Why little m data sets and not just one? The answer is we need that uncertainty in the missing data. The m data sets drawn across the whole algorithm, or the chain of missing data sets that we've imputed, allows us to have variability for our missing scores. The variation between imputed data sets captures our uncertainty about the missing values, and that helps us basically unbias, if you will, our point estimates and our standard errors. So, the chained equations approach, this is fully conditional specification. That's what FCS stands for. Sometimes you see that acronym. It initializes filling in starting values for all data. Again, I sort of walked through this before, but I'll say it again. Then for each variable, it fits a model predicted on all other variables. It draws from the predictive distribution for each missing data, and it replaces missing values with those draws. And we repeat this for many, many cycles until convergence, basically stabilization of our parameters of each model. and then we return all of those imputed values. Now, each variable can have its own imputation model, and this is what makes this much more flexible, because if you don't have fully multivariate normal data, no problem. You can use a logistic regression for some of these models. You could use linear regression. Basically, any model can be part of mice, which the mice process, which makes things very, very flexible and very useful. So in R, there's actually a package named mice you can download, which is very convenient to use. Here are, again, our example with missing data where we have x1 predicting x2 and y, and then x2 predicting y, and missing data on x2 and y conditioned on x1 here. What this tells us is we're going to grab 20 multiple imputations, and this is just basically what the predictor matrix looks like. So in this process of chained equations, we will look at x1. x1 actually has complete data, but we may end up using its regression just for the heck of it. We'd predict x1 with x2 and y. Then we would go to x2 and predict its value with x1 and y. And then we go to y and predict its values with x1 and x2. Here is how we assess convergence. This is the mean of variables x2 and y across the multiple iterations of the change. You can see the means are varying slightly. That's what we would expect. That's the uncertainty of the missing data that we're looking for. And here, what we can end up getting is an estimate of our prediction of x2 with x1. So our predicted estimate here of 0 and our predicted slope of 0.55. You can see the standard errors and the p-values as well, too. This is the pooled estimates after phase 3. And this is also the pooled estimates for our prediction of y with x1 and x2 itself. The other thing that this process gives us is a fraction of missing information, which is the proportion of cases that sort of impact the data themselves. You can have what proportion of cases tend to impact us on each variable as well. That's a topic for a later time as well, too. And here you can compare the point estimates for each of these. You'll see that mice and FIML in this case work very, very similarly themselves, and the values are very close together for what we have. All right, so that's mice. Let's talk a little bit about practical guidance and wrap up this quick overview. So which method should you use? Well, if you're using an SEM or a path model, particularly in Lavaan, you can just set missing equal FFIML in there, and it will work. It'll work great for the most part. If you're using regression or some multi-level, some generalized models, or you have mixed data types, the mice package will work very nice. Mice package is also good for exploring missing data and assuming or checking different distributional assumptions. Now, if you have missing not at random, though, if that's outside the scope of this lecture, there are some methods for it, but those are also very difficult to use. But importantly, never use a mean imputation in primary analyses reported in a peer-reviewed paper. If anybody suggests it, just cite Little and Rubin and explain why. Bad, 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 bad. So there are some key assumptions to check as well. We have to justify the use of missing at random. I would say the justification of this is we can get methods that work pretty quickly and that do a good job for missing at random. That is usually my justification overall. We do need to check for mice convergence, those trace plots that we show, so we see no trends across iterations. If we don't see convergence, we'd run more iterations until we got convergence. And we may also need to inspect our imputed values. Do they look plausible? Are they within the range of variables? So for instance, if you have a bounded variable, we may be imputing outside the bounds. That is not good either as well. You want to report what you did, basically, also, so that somebody can follow the methods as repeated. When you use missing data, because of the random process, particularly in impute chain mice, with the random process, it's not guaranteed people will be able to replicate results exactly. Even if they have your own machine, they'd have to save what's called the random number seed for random number generation. But even then, if they change their machine, they change their architecture, they change their computer, the seed may not carry over. So it's important to describe how missing data were handled and methods that you used for it. And you may need to check about sensitivity to missing not at random, although that seems to be a bit more rare. So this has been a nice, I don't know about nice, but brief lecture, nice and brief, let's put it that way, on missing data. Once again, there are three mechanisms that we widely recognize missing data fall under: missing completely at random, right, the coin flip; missing at random, meaning missingness is involved in some of the data you've collected; and missing not at random, which is missingness is due to things you didn't collect. And the mechanisms determines which methods are valid. You could say that, particularly for missing not at random, but generally speaking, we base our methods at missing at random and hope for the best. There are naive methods that are used that provide biased or inefficient method results, unless you assume missing completely at random. That's why we like to avoid those almost at all costs. I think that knowledge of that has gotten much more widespread, but you still see it from time to time. FIML is a preferred approach within path models. It uses all the data available without multiple imputation. And MICE is a general purpose multiple imputation framework. It's flexible, transparently, and widely applicable, and I highly recommend it. But once again, both of those methods I showed today assume listing at random. So this is it. Thank you for listening.